Okay, so let's look. We have found the generating function of our sequence. Unfortunately, the goal of our sequence was to, or the goal of finding the generating function was to know what these a of n values were. And we haven't done that yet. So in order to do that, we're going to need to do a little bit of algebra and a little bit of calculus. So let's start with the observation that g of x is equal to x times 1 minus x over 6x squared. Now I'm going to try to factor this, and when I do, I will get that g of x is equal to x over, let's see, 1, 1, and these signs have to be different. 6x squared can factor as minus 3x plus 2x. So I have to factor this like any other quadratic polynomial. It's a little bit awkward because it's written in the opposite order of what you might expect. But if I factor it, I get to here. That's good. Now I need to remember, wait a minute, I can do partial fractions on this. So if I start doing partial fractions, I get to a over 1 plus 2x plus b over 1 minus 3x. I don't know what a and b are, but in a minute I'll go through solving for them. Now why would I want to do this? The reason I would want to do this is that this looks a lot like 1 over 1 minus x. And 1 over 1 minus x is something that I know how to work with. I know exactly the sequence of coefficients on 1 over 1 minus x. So, we're trying to figure out what a and b are here. So, a quick review of partial fractions, and I'll do a longer one if we need it. But if I got this and I got a common denominator, this would be equivalent to what I started with. So this would be a over times 1 minus 3x over 1 plus 2x, 1 minus 3x, plus b times 1 plus 2x over 1 plus 2x, 1 minus 3x. And all of this should be equivalent. So the denominators are equivalent. I have x over 1 plus 2x, 1 minus 3x equals a times 1 minus 3x plus b times 1 plus 2x all over 1 plus 2x, 1 minus 3x. You do not need to write all this down. Rather, what I would suggest is that you just know that this is how the process works, and then at the end of it, the conclusion is x equals a 1 minus 3x plus b times 1 plus 2x. If the denominators are equal and the expressions are equal, then the numerators have to be equal. So I'm going to work from here. And there are a couple of different ways that people like to use to solve this. So I'm going to start, I like to use the plugging in method. So if I plug in x equals 0, I get 0 equals a times 1 minus 3 times 0 plus b times 1 plus 2 times 0. So I get 0 equals a plus b. And then if I plug in x equals 1, I'm going to get 1 equals a times 1 minus 3 plus b times 1 plus 2. So 1 equals negative 2a plus 3b. So what I've done here is I plugged in x equals 0 to get one equation, and I plugged in x equals 1 to get another equation. And now these two equations are ones that I can work together to solve. I know how to solve 0 equals a plus b, and 1 equals negative 2a plus 3b. There are lots of ways to solve systems of equations. In this case, I'm going to use substitution. From this equation, I get a equals negative b. If I plug that in here, I get 1 equals negative 2 times negative b plus 3b. And that gives me 1 is equal to 5b. So that means that b is equal to 1/5. And then going back to this relationship, that means that a is equal to negative 1/5. So I have my two coefficients. So going back to my partial fractions, that means that g of x is equal to negative 1/5 over 1 plus 2x plus 1/5 over 1 minus 3x. And we know what these expressions are. This is the sum. So I can pull this negative 1/5 out front, and I'm going to. It's negative 1/5 sum from n equals 0 to infinity of negative 2x to the n plus 1/5 times the sum from n equals 0 to infinity of 3x to the n. And so this is equal to the same thing as if I had sum from n equals 0 to infinity. Let me bring this back in. Negative 1/5 times negative 2 to the n, x to the n, plus 1/5 3 to the n, x to the n, or sum from n equals 0 to infinity, 2 to the n plus 3 to the n over 5 times x to the n. And at the very beginning of all this, we said this must be equal to the sum from n equals 0 to infinity, a of n x to the n, which means that this has to be equal to this. So we have found a closed form expression for our sequence, the one that satisfies the recurrence that we started out with. The actual answer here is a of n equals 2 to the n plus 3 to the n over 5.